Okay, so it's recording now. Today, the seminar will be in English because we have some friends, international friends that are participating, in particular collaborators of Sergio. And our speaker today is Professor Sergio Jorás from UFRJ. And Sergio did his undergrad studies in physics at PUC in Rio. And then he moved to CBPF for his master degree, and then moved to UFRJ for his PhD. After that, he went for postdocs at UERJ, Brown University, and UFRJ. After that, he spent 3 years in the south of Brazil as a professor, but then he came back to Rio in 2006 as a professor at UFRJ, where he is based until today. Sergio was associated member at the ICTP in Trieste for, I think, 5 years. And he is a specialist in modified theories of gravity, dark energy, inflation, and related topics. And today he's going to talk about F of R theories. And I would like to thank Sergio again for accepting the invitation. And it's a great pleasure to give you the floor. Thank you, Sergio.
Thank you, Antonio. It's a pleasure for me to be here. And I apologize again for having asked you to postpone the seminar a couple of times. But finally, here we are. So this talk is based, the most large part of this talk is based on these papers down here. This is the paper that I published with Cesar. He was then my PhD student, and his PhD thesis is also available online, where you can check the details of the calculations. So let's start with general relativity. So usually we write the Lagrangian as a function of the Ricci scalar, which is the simplest scalar Lagrangian that we can think of. And of course, we can add an action for whatever matter or radiation field we want. And then you just go through the standard procedure of just varying the Lagrangian with respect to the metric. And then you end up with the Einstein equations, right? And then if you take the trace, then you got an identity between the Ricci scalar and the trace of the G mu nu, the energy momentum tensor of matter or radiation or whatever you want to put on this right-hand side, right? But so one may think of what would happen. Okay, sorry, before that. So this is it's just a Bianchi identity, right? The divergence of capital G mu nu is vanishing, right? And so is the right-hand side. So the G mu nu is conserved, right? This is an identity in GR. So what happens if we change this Ricci scalar by a nonlinear function, and then we go through the same procedure? We have a slightly more complicated version of Einstein's equations, the so-called modified Einstein's equations. And here f sub r is just the derivative of f with respect to r. And of course, in GR, then you get back to the usual Einstein's equations, right? Because all these extra terms, they just vanish. But if you take the trace of these more complicated equations, then you have this equation down here, and you can see that it's not an algebraic equation, it's just a differential equation for R, or a differential equation for the metric. And it's actually a fourth order differential equation for the metric that's going to be make a huge difference in the next pages. But you can see that here, the trace of G mu nu only acts as a source for this differential equation, right? So as I said, if you start with a nonlinear function f of r, then you have a fourth order differential equation for the metric, because R itself is already a second order differential equation for the metric. And so with the Lambertian here, we have a fourth order differential equation. Right? But however, you can look at this equation as a second order differential equation for f prime, f sub r, right? So if we look at it, at this equation, this Lagrangian, as a Lagrangian transformation, then you can write this fr as f prime times r minus u, where u is this transformation, right, on f. So phi, if you just define it as a new variable phi as f prime, then you can see that u is just a transformation on the original f. So f can be seen as a transformation on u, right? So that's just exactly what happens when you go from a Lagrangian to a Hamiltonian, right? We just have twice as many equations, but we have, instead of having second order differential equations in the Lagrangian variables, we have first order differential equations for the Hamiltonian variables. So that suggests that actually the best variable to work with is actually phi, which is f prime, right? So we can think of making a change of frames, and you go to the so-called Einstein frame. So there is a nice review by Sotirio and Faraoni, but it has already been done before by Mangano and collaborators in the 1990. So I strongly recommend these two papers. So let's just recall that if we had been working with purely affine theories, I mean that in theories that we don't have a metric to start with, we have only the affine connection as a fundamental variable. In those theories, you can define a metric just by making the Lagrangian, just making the variation of the Lagrangian with respect to the Ricci tensor, and then dividing by the square root of the determinant of the same matrix, the same derivation. And then we end up with the metric. So what Mangano has suggested that we should use this as the fundamental definition of the metric, let's call the correct metric if you wish, when L is f of r, is not the Ricci scalar. Of course, if L is just, the Lagrangian is just a Ricci scalar, actually square root of minus g times the Ricci scalar, then this is the metric. There is nothing new here. But if the Lagrangian is square root of minus g times f of r, then we end up with something different. Then if we do go through this calculation over here, then we calculate a new metric, which is just f prime times the original metric. And then that's where the conformal transformation begins. So let's make this conformal transformation on this metric, on this Lagrangian over here, and then we end up with the so-called Einstein frame. So if we define this as a new metric, where chi is just f prime, and then just define a new field phi, which is actually the logarithm of f prime, then that Lagrangian, which was just f of r, is written like this. So we have the Ricci scalar calculated in this metric, tilde g mu, right? So that's what's called tilde r. And you have also an two extra terms, which is the kinetic term for this phi field, the new phi field, and the potential that is defined as a function of the phi field itself. So, once this f of r is defined, then you have a perfectly well-defined new metric, because the conformal factor is just f prime, and you have new field phi, which is basically just the log of f prime, and you have a totally well-defined potential for this phi field, right? Which defined as in terms of f, right? So that's one way to see, to make this extra degree of freedom that f of r theories have, concrete. So this phi field is just this extra degrees of freedom made concrete, right? So it's written explicitly in this way in the Einstein frame. But just to have to remind ourselves that any extra actions like matter or radiation fields, they are going to follow geodesics in the original Jimmy New metric. So when you write this action over here, it will look like that this matter fields or whatever you want to define, they won't follow the metric in this tilde Jimmy New metric. So it will look like there's an extra force. So it's equivalent to say that the Jimmy New, the energy momentum tensor for the matter field is not conserved if you calculate its divergence with respect to the tilde metric, right? So it's conserved only in the original metric in the Jordan frame, not in the Einstein frame. So that's where we define the T mu for the matter field. So at the end of the day, we have to go back to the Jordan frame where energy momentum tensor of the matter, radiation or whatever, is conserved, and that's where we make the calculations and that's where we make the observations, right? So this is pretty much standard. So we go from, so in a nutshell, we start in the Jordan frame where we define a nonlinear function for the rate scalar. So we may have in the back of our minds solving, generating an inflationary period or generating a current accelerated expansion of the universe, or just for the sake of the argument to investigate different theories of gravity. So whatever the motivation you have, you can think of different equations for the metric, for the gravitation, right? For your gravity theory.
Sergio?
Yes?
Sorry, I think you stopped to share your screen.
Oh, sorry, let me do it again. Sorry for that. Is it okay now?
Yeah.
Okay, so where was I? So we start in the Jordan frame with this nonlinear function of rate scalar for whatever reason, and then go through these two transformations, the conformal transformation and the redefinition of your extra field. And then at the end of the day, you have this Einstein frame where you have an Einstein-like Lagrangian for the gravitation, and you have a Lagrangian for your extra field, right? With a really well-defined potential, right? Is this one. So the question that Cesar and I asked ourselves was, what happens if we work the other way around? I mean, we start in the Einstein frame with a given potential. So how can we define the function f that corresponds to this potential over here? And then we realized that it had already been done before by Banano. So we started with a really simple potential, the phi squared potential, and later we added just a trivial shift, the vacuum value, and we added cosmological constant. Initially, it was just for the sake of completeness, but it turned out to be really essential for our picture, as you will see in a few minutes. So as I said, it had been done before by Bagnano in this really nice paper in '94. And then you have a parametric form of f of r. So f is defined as a function of your phi field, so is r. But once it's done, you can just parametric plot f as a function of r. So there's no big deal here. So before showing what happens if you choose this v and showing you f of r, let me just remind you of a few constraints that any f of r theories are supposed to hold. Actually, this is a really nice paper, but what was where these constraints were compiled by Pogosyan and Silvestri. And so they write your f of r as a gr Lagrangian plus a deformation. And so they claim that in whatever delta function you have, it must follow these three constraints over here. But I'm really concerned about this first one, because the usual argument goes something like that. okay, you want to recover GR at early times because you want to be able to explain the radiation-dominated universe and the matter-dominated universe. So you just want to use FFR for explaining the current accelerated expansion of the universe, for instance. And then it sounds reasonable, right? Because when you go to large R's, which in GR corresponds to large densities, then you would like to get rid of these extra terms, so you have something that is really close to GR. But actually, the problem is that only because the Lagrangian is close to the GR Lagrangian, that doesn't mean that the solutions of the equations of motion are going to be close to the solutions in GR, right? So, second of all, it's not necessary to have a large Ricci scalar at early times when rho is large. Obviously, you know that the energy density is large, but in FFR theories, it doesn't mean that the Ricci scalar is large. Remember that there's no algebraic relation between R and T. There's only a differential equation. So rho is just the source for the evolution of R. So it doesn't mean that R is going to be large when rho is large. Actually, I'm going to just show you one case that it's not. It's actually, R is really small at early times. And second of all, we do know that Starobinsky's function, R plus alpha R squared, does not go to GR at low redshifts, at low redshifts or low Ricci scalars. We know that by this paper by Amendola and collaborators, that this Lagrangian by Starobinsky is really useful to explain to generate inflation, for instance. But even after that, this extra term has to be turned off completely, because otherwise it will spoil the whole evolution afterwards inflation. So you could think of that for low R, this extra term would not be as important as the first one, because it goes to zero really faster than the first one, because it's R squared. But that's not so. Amendola has shown that after the radiation-dominated universe, if you keep that term, you don't have a matter-dominated term that would last as much as it would have to, just to grow, to allow for growth of cosmological perturbations. So that's actually a really counter example for this first rule, which is taken for granted for many authors. And on the other hand, this third constraint is really useful. It says that the second derivative of your f, right, of the new Lagrangian, should be positive. Otherwise, your background solutions would not be stable. It's called no tachyonic constraint, which is reasonable. But I'll show you in a few minutes that that's okay to happen just as long as it doesn't last too long. So if there is an instability, but it's only temporary, that's actually okay. So let me show you, going back to the problem that we are studying, what we have in mind is just to generate inflationary solutions. So it can be shown that if you have inflation in the Einstein frame, you have inflation in the Jordan frame as well. So let's start, as I said, in the Einstein frame with that potential, quadratic potential in phi, and start with slow roll initial conditions, because that's what we have in mind. We would like to generate inflation in the beginning of the universe. So we set up the conditions for the phi field. We have an initial phi, we have an initial phi dot, and then later on, the field will oscillate at the bottom, around the bottom of the potential, of its potential, right? And eventually will reheat the universe. But of course, this oscillation is damped because of not only because of the reheating process, but also because of the expansion of the universe, right? It damps away the energy in the phi field. But right now, we're not concerned with this reheating process. This is a whole other history. Right now, I'm just concerned with the previous phase of the rolling down, the slow rolling, and the fast rolling, right? So there is no matter in our field. The right-hand side of the Einstein's equations, the modified Einstein's equations, are zero, right? So once we have the solution of this phi field, then then we do have, because just a scalar field rolling down a given potential, right? And it's in an extending universe, so it's pretty standard to calculate the time dependence of the phi field. Then you just have to plug it in. So you have f as a function of phi as a function of t, and you have the Ricci scalar as a function of phi as a function of t as well. So you do have f as a function of r at the end of the day. Right? So that's what I'm going to show you. So that's phase one, when you have the initial conditions here. So this is f as a function of r for the trivial case, no cosmological constant and no shift in the vacuum solution for the phi field. So in the beginning, when the phi field is large, negative and large, and slowly rolling down the hill, so the Ricci scalar starts 0 and grows slightly, and then gets to a maximum, and then goes down when the phi field starts to roll, fast roll downwards. So the roll parameters break down at some point down here. And then when the phi field is oscillating at the bottom of its potential, R is oscillating as well along this line over here. And this dashed gray line is just F equals R, so it's GR, right? So it oscillates around here. It's a dampened oscillation, of course. So let me just call your attention to the fact that you do have positive second derivatives in the first branch and in the third branch as well, but you have a negative second derivative here. The curve is concave over here. So it seems that it shows that the system is unstable, but it's really just a phase. So it goes through this instability, but really quickly. I'll just show you a few animations. So this is an animation. So this is in blue is the Ricci scalar, in red is the phi field. So the Ricci scalar goes to a maximum value. You can see over here and on the left as well. And then only after the Ricci field goes to maximum and the minimum, then the phi field oscillates around the bottom of its potential. And you can see on the left-hand side, the Ricci scalar oscillating around 0 in the last phase. So it goes through along. It's just repeating itself. And the bottom panel is just a zoom in this first branch over here. So I can show you that it's not linear. It's actually almost quadratic evolution, right, over here. So let me just point out that in this first phase, R equals 0 is unstable. So the system moves away from R equals 0. But in the last phase, R equals 0 is a stable solution. So there is a change of stability here somehow, right, for R equals 0 solution. And then we can play the same thing again. It's not animations, but you can just plot f of R for different values of the parameters, lambda and a. So this is exactly the previous one that I just shown you. And this is for R a equals 0.2. So there is a change in the derivative, right, in the slope of the curve over here. And you can see there is a change on scale. On the vertical axis that corresponds to a change in the slope, right, of this curve. And so if we increase the cosmological constant above a critical value, then this unstable branch is missing, right? And so if we change A or 0, that changes both of them. It can make this unstable branch disappear, and it change the slope of the curve around the final value of the Ricci scalar. Actually, the change of slope is really important because we can write the Lagrangian as a perturbative solution, the third branch, right, around R equals 0, because it does oscillate around that. And then we have a constant value plus something that is linear in R. This constant value is just something that it's actually proportional to the cosmological constant that we had in the Einstein frame. So, and actually the value of this effective cosmological constant depends on A. So if A equals 0, you have this exactly the same value, but A could be large and negative, so this effective lambda would be really small. However, we do have something multiplying the Ricci scalar here, which has the same exponential behavior, which means that you could in principle absorb this extra constant factor in an effective Newton's constant, and that will actually change the value of the Newton's constant in the other way around. So if A is large and negative, then this effective cosmological constant would be really larger than the original value. So there is a trade-off here. So that's...
Sergio, can I ask you a question?
Sorry. Sure, please.
So you are showing different values for these parameters, lambda and A. I'm not sure in which units you're measuring lambda, but let me ask you one thing. If you have a tiny value for lambda, do you know if this behavior is I mean, because there is a qualitative difference between lambda equals to 0 and lambda equals 1.2. If lambda is tiny, does this behavior change qualitatively as well?
Well, there is a critical value of lambda where this happens. I can show you in this picture over here. There's a 3D surface, right? It's f as a function of r as a function of lambda. So in these units, that happens at lambda equals 1. So for lambda larger than this value, there is a smooth surface f of r. And for lambda smaller than this value, then you have this, as I said, the unstable branch over here that just vanishes above this critical value of lambda. So I'm not claiming that it's actually the right value of lambda, this effective lambda or anything like that. I'm just saying there is a critical value of lambda with different qualitative solutions for f of r.
Yeah, I see. Okay, thank you.
Okay. So as I said, this is the unstable branch, right, with the negative second derivative of f. And this is the same curve, which just rotated a little bit. So lambda f is now this horizontal axis. I just rotated the figure just because it looks really similar to this plot over here. And this plot is just the Gibbs energy of a van der Waals gas as a function of the pressure and the temperature. A van der Waals gas is just a non-ideal gas, the first one that we learn in thermodynamics or maybe physics, basic thermodynamic physics course. And it just takes into account the interaction between the particles and actually the space that they actually occupy in the volume. So there is an effective volume and there is some interaction between the particles. And so you can see that they are actually pretty similar if you just map F to P, R to G, and lambda to T. And actually that's the mapping that we have, right? And actually that makes some sense because F is our Lagrangian, right? And we can actually look at this Lagrangian instead of, oh, okay, no, this is just a theory of gravity Lagrangian, but no, we can look at this Lagrangian as just a pressure of some fluid, right? If you can go and write the Lagrangian for some fluid in general relativity, the Lagrangian is going to be the pressure of this fluid. So that's why that's another way to look at it. We're not looking at it as a theory of gravitation or anything, you're just looking at this Lagrangian as the pressure of some fluid, right? A perfect fluid, right? And then, since we do know the function of R and F and functions of phi, that means that we do know the Gibbs energy of this fluid and the pressure of this fluid and the temperature of this fluid as a function of the phi field, right? And actually, another piece of information that's really interesting is that these unstable branches are also nicely corresponding, right? Because that's the unstable branch, and so is this unstable branch for the van der Waals gas as well. And this branch over here, these wings, right, just below that, they are the metastable states. I'm just going to show you a picture of the pressure as a function of volume that will ring some bells, hopefully, for you. And everything else is just the stable solutions, right? So we do have, in the van der Waals case, we do have a description of some fluid that behaves as a gas for large temperatures or large volumes, and as a liquid for small temperatures and small volumes. So we do have two different phases here. And you can see that no matter which frame we have, if you look at the Einstein frame, for instance, remember that we have the phi field and the V of phi right here. So the Lagrangian is just the Ricci scalar with a tilde here. There should be a tilde because that's the Einstein frame Ricci scalar. And this is the exotherms, right, from the phi field Lagrangian. And we can actually define a equation of state parameter for this phi field as P over rho, as usual. And then we can plot the evolution of this equation of state parameter as a function of time, because we do know phi of t, right? So we do know phi dot as well, of course. And then it starts around -1 because that's what we chose. We have chosen the initial conditions that were suitable for inflation. So it should be -1, right? So it agrees with what we wanted. And then later on, it just oscillates around 0 because that's what the phi field does. It oscillates around the bottom of its potential. And if you calculate the average value for this phi, of this equation of state parameter, it does go to 0 as time goes by. So that's something that has an equation of state parameter -1 and goes to 0. So that's the phase transition, right? The equation of state changes qualitatively at some point over here, right? And if we go to the Jordan frame, we do have a change of equation of state as well, because we can define a curvature fluid and we can define a pressure, a curvature pressure as well. There's more than one way to define those things. They are not uniquely defined, but in this definition over here that we had used before in cosmology, we can define the equation of state parameter as before, right? And then it goes to -1 in the beginning as usual because we also have inflation in the Jordan frame. And then later on, it goes to something that diverges just because the energy density vanishes eventually with some periodic behavior, and so does the pressure, but they do not vanish at the same time. So we have some divergences here just because they vanish at different times, rho and t, but that doesn't mean that anything physical is actually diverging. Everything there is actually well behaved. But this parameter over here is not well defined whenever these two vanish in different times, right? But still, we do have different behaviors for the fluid in this phase and in this phase over here. So that's a phase transition again. And on the other hand, if you look only at the van der Waals gas description, we can actually define, for instance, density, which is just proportional to the inverse of the volume. So kappa here is just a function, just a parameter, a positive parameter, just so we are able to define rho because we only have v, right? And then we can define the sound speed for this van der Waals gas as p dot over rho dot. And just is something that's just proportional to p dot over v dot, right? And then we do know p and v as a function of time, and then we can plot the sound speed squared in this as a function of time. So never mind the values over here because the numericals actually depend on the value of kappa, and we do not know the value of kappa. It's just the sign that bothers me, the sign that's really interesting. So if you have lambda equals 0, which is the trivial solution, the very first plot that I showed you, you have a huge unstable branch, then you have this range of time where the sound speed squared is negative. And actually that actually corresponds to this point over here. We can map the time where the phi field goes to this value and this value over here that defines the unstable branch. They actually correspond to these 2 points over here. And we can actually see that also because for a critical value for this lambda or above, for the critical value of lambda, this curve touches the 0 axis. So that's the critical value when this unstable branch vanishes. And above that value, we don't have this touch. So the sound speed squared is always positive. So we do have, there is no second branch. We have that other plot that I showed you before. So As I said, we do have really nicely defined functions for the Gibbs free energy, and of course the pressure, and of course the volume, right? Because the volume is the conjugate variable to the pressure when you talk about the Gibbs energy. And so we can also define the phi field as a function of the volume if you wish. And another really interesting piece of information is that this volume over here is just, volume is just f prime, which is actually the conformal factor that changed the form from the Jordan frame to the Einstein frame, right? And so since we have p as a function of v and we have v as a function of phi, we can invert this equation, as I said, and just plug it back here in p. So we have p as a function of v as a function of the temperature. So that's the equation of state for this van der Waals gas. And actually, it's not exactly van der Waals gas, because if you take the limit for large temperature, then you have T over V squared, which is not V. So it's not actually van der Waals, should be T over V, but that doesn't matter because it does have the same behavior, the same qualitative behavior as a van der Waals gas. So it's not an ideal gas limit, but who cares? We're not expecting, it doesn't have to be an ideal gas limit, right? So this is the curves. These are the curves, P as a function of V for different values of the temperature, this expression over here, right? So for large temperatures, temperature is the cosmological constant here, right? We have a sort of ideal gas-like behavior, right? For this thick black curve over here, that's the critical temperature. We start to have this the second derivative change sign over here. And of course, for smaller temperatures, we do have these other curves over here, right? So these curves, the blue and red ones, are the binodal and spinodal curves. So let me just remind you of what these curves are. So this, the inside here is just exact van der Waals gas. So we cannot see any difference between these two plots, right? Because the only behavior instead of 1 over v is 1 over v squared, which qualitatively is just the same. We cannot see the difference between these two plots over here, right? So it doesn't matter if it's van der Waals or something really similar to van der Waals. It does have all the same features, which are, as I said, the binodal and the spinodal curves. So the binodal curve is just defined by the Maxwell construction. The Maxwell construction is just that the pressure that the system actually follows from going to the gas state to the liquid state, or the other way around, doesn't matter, as long as this area over here is equal to this area over here. So for a constant temperature. So the integral of P as a function of V, the integral P dV, is actually the Gibbs energy. So that's why at this point over here corresponds to these 3 dots over here. You have the same, if you wish, chemical potential or the Gibbs free energy. They are the same thing here. And so that's the pressure that the system actually goes through if you're going from a gas state to the liquid state, right? So if the system is below this curve over here, so in this region over here, or in this region over here, where the derivative, the PdV, is negative, so the system, you can say that the system is supercooled, for instance, just like that liquid that is really, really cold, just below the freezing temperature, but it is stuck in a local minimum of the potential energy. So just have to give just a little bit of energy, so it goes through that small hill and then freezes all over. So that's the metastable states, right? This region over here, in this region over here, until the extrema, right? So below the blue line, that's just the metastable configurations that correspond to this branch over here and this branch over here. And the red line is the spinodal curve that shows the unstable configuration that corresponds to the region where the PdV is positive. And if the PdV is positive, it means that the configuration is totally unstable. And that corresponds to the second derivative of dg dp being positive. as well. So there is that's an identity. To say the PDV is positive, it means that the second derivative of g in terms of p is positive as well. So between in a nutshell, between the blue and the red curves, the system is metastable, and below the red curve, the system is unstable. So let's see what happens in our picture. Remember that we have, in the Einstein frame, we have set up the initial conditions for the phi field to generate inflation, right? And that actually corresponds here to a large volume. So the system starts over here, let's say in this curve over here, it starts in this region, in this value. So it's a metastable region between the blue and the red lines. And that's actually really good, because we do want inflation to last for a little while. It cannot be just instantaneous inflation. That wouldn't solve any problem whatsoever. But on the other hand, it cannot be stable, because otherwise it wouldn't end, and inflation has to end. So metastable is just the definition of the inflationary phase, right? So it starts over here. It's, let's say, in this curve over here, the metastable region, and it goes here, following a constant temperature curve, right? Goes through the unstable branch, the second branch that I showed you, and then ends up over here and oscillates around this very point over here. So that it oscillates around the back and forth around this binodal curve, right? And of course, since we do have thermodynamics, we can have the whole thing. We can have the Helmholtz free energy, so that's defined as a function of V and T. We can calculate the entropy, and it turns out it's only a function of the volume. And we can actually calculate the entropy as a function of temperature and the pressure, instead of just a function of the volume. And we can plot this binodal line and the binodal line over here. And you can see this binodal line is actually defined, it can also be defined by catastrophe theory, which shows exactly where this the solution is turned from stability to instability. So we can actually calculate this curve and plot over here, and we can show that it triggers the appearance of stable solutions over here. So it actually was calculated and was also as we expected. So there is this is calculated for our problem, but you can see books that describe van der Waals gas in terms of the catastrophe theory, and this is exactly the same thing. Yeah. And the binodal curve is just in between, because it shows when the liquid phase, one phase, starts to be more stable than the gas phase. So there's a change of the actual true vacuum of the theory when you cross the binodal curve. As I said, you can keep calculating things from thermodynamics. We can calculate the internal energy, you can calculate the specific heat at constant volume, and you can actually calculate, which is really interesting, the specific heat at constant pressure, because it does trigger, shows that there is a phase transition, a first order phase transition as well. So these curves were calculated. So we can be above the critical pressure or below the critical pressure, and we know that at the critical pressure, the CP diverges as a function of the temperature. So that's exactly what we got here, and we have this exponential, the critical exponent around 1, which is really nice to calculate. So let me just wrap up what we have learned so far. So we started requiring inflation in the Einstein frame. So we set up initial conditions for the phi field just to generate inflation, which is metastable as it should be, since it should end. And that's what happens in this first branch over here, which is actually something that is not linear, it's actually quadratic, but it's not Starobinsky. The best fit for this curve is not r plus alpha r squared, it's actually r to 2.2 power, which is something different from Starobinsky, right? So, as I said, instability is not bad because it's temporary. So we should not discard any theory just because the second derivative is negative, because it can be negative just for a while, right? And it's really good. I'm just going to tell you why it should be negative. And let me just remind you that we all over, we did not have any matter or radiation or anything on the right-hand side of the Einstein's equations. So the energy density is 0 for all times, but the real scalar was not. So it started vanishing in the really early universe. It started 0, and then goes to a large value and then a negative value and oscillates around 0 just because we do not have matter. So at some point, we do expect that the system interacts with matter, right? The gravity interacts with matter because we are here, and then that's something that we are studying right now. So something that Cesar and I have been doing is studying different potentials, so a quartic potential, 5 to the 4th, and also a double well potential. Actually, a double well, which is really nice, because actually the solution depends on the value of A. If A is really large, then this barrier is really large, and the system is stuck in the very first well. So everything looks really similar to just one well potential, the quadratic potential, or the quartic potential actually, just because the system does not even see the second potential. The system does not know there is a second well. So the system goes from a really large negative phi and oscillates around this first well without ever probing the second one. So there is no much new here, nothing. Well, qualitatively it's not new. But what happens really interesting is when A is really small than this critical value. Okay, just before that. So we can plot f of r. That, as I said, is just a function just as before, but we have a really different value for the first derivative here. So there would be, this is what gr would be, the dashed black line, and that's actually what we have. So we have a different gravity, a different value for the effective Newton's constant, just because a is not 0 over here. So what happens when A is really small? This barrier is smaller. So the system, the phi field goes from goes from a really large value, a negative value, probes the first well, and then goes to the second well, and it oscillates around the second well. So that's a really different solution from the previous one. And then if we plot f as a function of r, so we do have the first branch over here that you can barely see because it's really almost flat. So it coincides with the horizontal axis. But then as before, it reaches a maximum and then goes to an unstable branch and then has a stability branch again. But then there is a second unstable branch over here and then a third stable branch over here, and then it oscillates. That corresponds to the second well. And this one corresponds to the first well. Right? So there are actually two catastrophes here, and we're having a really nice time trying to discuss that, because if we plot P as a function of V as before, so you have, instead of having one critical temperature below which you have instability and binodal and spinodal curves, we do have 3 different critical temperatures. And so we are having a really nice time trying to describe what happens and trying to calculate the binodal and spinodal lines. It's been really fun to do that, right, Cesar? So what have we been doing also? So we are starting, Saikat and I are studying the growth of curvature perturbations. So previous results by Carloni, Dunsby, and Troisi, they had studied what happens in f of r, that's a power of r, just a power. And they have shown that the super-Hubble modes, I mean, almost homogeneous modes, they grow even during the accelerating phase. So that sounds really weird and strange, but other papers have already replicated these results. So, but I think that we may have found the answer. It's because we are in the unstable phase, right? The stable branch. There is still some inflation in the unstable branch, and that means that the perturbations would grow exponentially because the sound speed squared is negative. So that's why the even super-Hubble modes would grow in this stage. But we still have to make these calculations within this van der Waals gas approximation, the thermodynamic approach, just to see if they match, right? That's what will be really nice, to see if the growth calculated from the point of view of just the van der Waals gas would match the growth coming from the modified gravity theories, right? Something else that we have been doing, Rich and Karim and I are working with, oh, sorry for the typo here, is radiation, of course, there's an extra A over here. So coupling to radiation in the Einstein frame, we could have some warm inflation in the Einstein frame. And then the temperature would not decay, so we don't have to have this reheating period after inflation. And coupling to radiation is really fine because radiation is conformally invariant. So the source term on the equation of motion for the phi field would be trivial because it couples to T, which vanishes. And then, so the equations would be really fine to work with. I mean, not fine, but easier than with matter, right? And then we are starting to study what happens with the radiation in the Einstein frame. And so what happens to radiation in the Jordan frame and what happens with the temperature in both frames, right? And what happens, of course, in the van der Waals gas scenario, in the thermodynamic scenario. And finally, with matter would be really, as I said, a lot more difficult because matter is not conformally invariant. And there could be some parametric resonance in the Einstein frame, but that would be really hard to map to the Jordan frame because of this non-conformal invariance of the matter field. So that's something that we are looking to do in the near future. And also, finally, with Sergio Duarte, Ribamar, Arbanil, and Juan, who was my PhD student, we studied the stability of stars. Then we wondered what would happen if we studied a very equivalent problem. Instead of having a homogeneous and time-dependent solution, as we have in cosmology, what happens if we have a correspondent solution, which is a static but spherically symmetric solution with this potential in the Einstein frame. So what would happen with a star in the Jordan frame, right? So we are starting studying the same problem, or not exactly the same problem, it's the equivalent problem. We start in the Einstein frame with a single well potential. And so we go back to the Jordan frame and study what happens with the star. So those are really preliminary results that just came out just a couple of days ago. So I have to double check that yet, but I couldn't resist in showing you these two plots. There is a mass radius diagram, and there are actually in the Jordan frame. So that's where we make the measurements. So that's the solutions that we have. So this looks like a pretty standard mass radius plot, right? And see there is something a larger mass, maximum mass over here, and a maximum radius over here as well. And you can see that we have this is a mass as a function of the central density of the star in the Jordan frame as well. So we do have this behavior over here with a maximum mass, a stable branch over here, and a stable branch. And you do have some extra solutions here that do look like a lot of noise, and they probably are numerical errors from our calculations, but I couldn't resist in looking at these solutions a little bit more. That's something that I really intend to do in the near future. But what is really interesting here is that we do have this f of r behavior. So we do have a first branch, we do have a second unstable branch with a negative second derivative, and then we have a third stable branch over here. So something that I want to do yet is just to check if this unstable branch over here, if they correspond to this unstable branch over here, right? We do know that for large central densities, this should be unstable. So it would be really nice to see if this unstable branch over here corresponds to this unstable branch over here. But that's something that we still have to check. And just to end, right on time, I hope. We have been studying thermodynamics of alpha-pi theories in single well, double well, and of course the next step would be a symmetry explicitly limited breaking with double well with non-equivalent vacua, right? There's plenty of stuff to be done in cosmology, supercooled inflation, standard inflation, warm inflation, the growth of perturbations, and of course with this thermodynamics picture. And finally, the stars with the full numerical evolution of the two of the equations. And the next step would be the study of stability in the series, right? Juan had nicely done in his PhD thesis, was studying the stability of f of r theories in the standard approach. There was no thermodynamics theory back then, so we have to calculate what is usually done. Calculate the frequencies and the frequencies squared of radial perturbations, and then we determine when these squared frequencies go negative, that triggers the instability, right? So that would be really nice to calculate that in our picture and see if that corresponds to this second unstable branch in f of r theories. Right? So thanks for your time. Thanks for having me.
Okay, thank you very much, Sergio, for this very nice talk. I would like to invite you all to open your microphones to thank Sergio for his talk.
Thank you, guys.
So we can get started with discussions and questions. So I saw that Satish raised his virtual hand before. So Satish, you can go ahead.
Thank you, Antonio. Thank you, Sergio. Great talk.
Thank you.
When you consider can you hear me properly?
Yes.
Okay, fantastic. When you consider the Lagrangian as a fluid Lagrangian, I thought it's a very brilliant move.
Thank you.
And so I'm tempted to write since their Einstein equations are nonlinear partial differential equations. So I would be tempted to write Navier-Stokes for that Lagrangian. So I wonder, if you write the Navier-Stokes, will there be any kind of correspondence between the Einstein field equations and the Navier-Stokes, right? Because such a correspondence exists in string theory. They do have the fluid gravity correspondence, right? So in that connection, I was wondering if you can find anything interesting, right? First thing. The second thing is, when you went to the gaseous limit, you did compute lots of things, Gibbs free energy, everything, right? But I didn't see entropy. Sergio, why did you not compute entropy?
No, we do have entropy.
Oh, okay, then I missed it.
Yeah, here it is.
Oh,
right?
There you go. Yes, I
as
missed
a function of the volume, of temperature and volume is like this, and as a function of the pressure and temperature is like that.
Okay. Fantastic. Great work. Congratulations.
And actually, let me just add that you do have a change of entropy, right? That might be related to a change of the phase transition, right? Might not. It is related to the phase transition, right?
Yes, fantastic. Thank you, Antonio. Thank you, Sergio.
Thank you.
Thank you, Satish. Now, according to Google Meet, the next one is Mauricio, Professor Mauricio. You can go ahead.
Hi, Sergio. Congratulations for the nice talk.
Thank you.
I guess it's fundamental for your results to have a relationship between the energy density and the volume in a certain slide. Could you show me it again?
Between the volume and what?
The energy density, rho, and the volume, right? In which you have kappa as well.
Oh, you mean when they're calculating the sound speed square?
Possibly.
There is
I guess it's essentially rho equals kappa over V, right?
Yes, that's here.
You are taking this this kappa. It's just a parameter independent of rho, V, and whatever other thermodynamic variables?
Yeah, it's just like the mass of this gas, right? So this a parameter with units of mass, so that I can go from v to rho. The sound speed squared is p dot over rho dot, right? And I know that rho is inversely proportional to v, but it's not actually 1 over v, right? There is a mass term.
Sure.
Right? So that's why I just added this kappa just for the sake of units, just to be correct in terms of
Okay.
terms, right? That's why. And so all I know about this kappa is just it's positive. So what I want to calculate here is just the sign of the sound speed square. That's that's the really important piece of information. The sign, not the value.
But that's the point of my question. For you to calculate the sound of speed when you are interpreting something as a fluid, you have to do, in fact, to make a choice of its equation of state, right? Because
Right.
it's whether it is an adiabatic, isothermal, or polytropical process, for instance. And
Right.
then when you choose, for you to calculate that p dot over rho dot, which
that's the equation.
Okay.
So I have G, I have P, and I have V. So I can just write P as a function of V, because I can write phi as a function of V, and then I have P TV.
And what kind of I guess it makes sense to ask what kind of, because we have, for instance, we have several, but at least two kinds of speed of sound. One of them is the isothermal, the other is the adiabatic one. Does it make sense? Which one have you calculated? It's the diabatic, or it doesn't make sense to ask this question?
Well,
because
it's a diabatic, because otherwise I would have to take into account the perturbations, the entropy, which I'm not.
So somehow in this derivative for the definition of the speed of sound, you are taking at constant entropy. Is that what you mean?
Yes.
Somehow you made this implicit
yes. Well, that's not my definition, right, of the sound speed squared. If you choose to fix the entropy, then that's the definition that you end up with.
Okay. Thank you. Perhaps just a fast comment. You mentioned that these choices of frames, so-called frames, it's something well established, and I guess it's not so clear-cut. There is still some papers in which people claim that you can use any frame and they should be physical, lead to the same observable consequences, and there are people who say only the Einstein one is the physical one, or the Jordan one is so.
I'm well aware that there are a couple of papers that debate on which one is physical, and both of them should be physical. I guess that the key word is equivalence, and that one has to be really careful when using these words, equivalence. Maybe some people want it to mean something, and the people that hear that mean something, that listen to something else, right? Equivalence is not a really nice word for that. It may mean different things for different people.
Yeah,
but I call the Jordan frame as a physical one, because that's where the range momentum tensor of the matter field is conserved. Right? That's Bianchi identity. So that's why I call it physical frame.
Okay. Thank you.
Thank
Congratulations
you.
again.
Thanks.
Thank you, Mauricio, for the questions. The next question is coming from Saikat. Please, you can go ahead.
Hello, Sergio. Can you hear me?
Sakai. Yes, yes.
Yeah, hi. So, thanks for the talk. So, I have some generic questions regarding these conformal transformations,
Yes.
which may be related to your presentation. So, if I take any scalar field potential, say, can you correspondingly make a Jordan frame FR Lagrangian, or there should be some uh, constraint on the potential?
You mean just this red line over here? This red arrow?
Yes.
No, you
Like
can. There is you can. There is actually a well-defined prescription to calculate that. I just it has been done in this paper by Magnano. So I just haven't written the expression over here. Have just written the result of this expression using this v of I that it's just in the first line. There is a well-defined prescription. It's just depending on v and v prime. That's it.
okay. So given any V5, you can make a Jordan frame Lagrangian. And
yes.
Do you know whether this correspondence goes beyond single scalar field case? Like if I take two scalar fields, like I know there are some models called assisted inflation models which have more scalar fields. So suppose I take two scalar field models. Now, can you can you make a conformal transformation and make it into a Jordan frame model which have FR plus another scalar field, as there is also some inflation model called Starobinsky-Higgs model, so which is like FR plus a scalar field in the Jordan frame. Now, yeah, I was thinking whether an assisted inflation model can somehow be taken back into an FR plus scalar field model similar to, maybe not the same as, but the similar to Starobinsky-Higgs model.
Yeah,
I mean,
understand.
I mean, that may be an idea. That's just a comment.
I understand your question, but I'm not sure if it can be done. I mean, I've never seen it being done, but that doesn't mean that it's not possible. What I do know is that some people, I guess Raissa does that. For instance, it starts in the Einstein frame with a given potential and makes a conformal transformation, but that's not related to this one. So here we have this conformal transformation that is defined by f prime, right? And that's not the only conformal transformation that you can make. But if it's an f prime, then you end up with an f of r. So if you can make this conformal transformation by a different function over here, and then you end up with something that is just not f. It's just another frame. It's a Jordan frame, but it's not an f of r that you end up with, right? So that's not your question. It's not answering a question, but that's just because I don't know the answer to that.
Okay, I mean, yeah, it's just an idea that came to my mind while listening to your talk. I mean, it's okay, fine. We can think about it later on. Okay, fine.
Sure. Thank you.
Okay, thank you, Saikat, for your question. I saw, now it's not here anymore, but I saw Thiago Caramês had a question. Yeah.
Yes,
you can.
I have
Yeah, you can go ahead.
I have to leave, so I have a very quick question to Sergio. Sergio, thanks for your talk. Very interesting. Your working you're doing with your students. My quick question is there any relation equivalent to second law of thermodynamics in this? So all the equivalence that you made with thermodynamics quantities, is there something that you can envisage some relation equivalent to second law of thermodynamics or not?
Well, I can tell you that when you evolve the system over here, for instance, let me just quickly go back to that plot over here, right? So what happens here is that you start with the system in this region over here, and so it has a large volume, and then it goes to a smaller volume. So that's the evolution of the system, right? So that corresponds. You mean it looks like it's just violating the second law because it looks like the volume is going down, right? So there is less. There is a smaller number of available states. But actually, the entropy here, I think it's here, it's -2 over V. So this minus sign you have to take care of. So there is, if you have, just think a little bit, because then you have something that is really small. Now I'd have to think more about it, Thiago.
Okay. Okay.
But it's a really nice question.
Okay. Okay. Thanks. Thanks for it. Thanks again.
Let me just write it down so I can get back to you.
Oh, sorry.
I'm just writing the question down so I can get back to you. The answer.
Okay. Thank you. Thank you.
Thank you.
Okay, so thank you, Thiago, for the question. And I don't see any further virtual hand raised. So I saw that during your presentation, you mentioned something to Cesar that you were having a lot of fun doing the calculation, and Cesar, said yes in the chat during that.
Yes.
Yeah, when Sergio talk about these three critical temperatures, we need to have this evaluation of this calculation. Is quite difficult right now.
Yeah, the problem is that we have the phase transitions for small volumes and for large volumes that we do understand, but in between we have something that is on the other way around. So we don't know how to define this spinodal curve in that region. It's been really fun.
I see. So Mauricio raised his hand again. Mauricio, do you want to say something?
Yeah, perhaps Sergio might be more explicit about what are the three cities you mentioned.
Okay, sorry, I thought it was obvious. Is the
Perhaps
Jordan
it
frame,
is.
the Einstein frame, and the thermodynamic picture.
All right.
Right. So of course it's a quotation of Dickens' book, right? Two Cities. So that's a third one.
Okay. So Alberto is also saying that he would ask the same.
You didn't guess either, Alberto. So you have to read your Dickens.
It's only two cities, not three cities. I would ask.
I know, it's just
one.
It's, okay, it's just poetic freedom. I just added the third one.
Okay. So thank you very much, Sergio, again for the very nice presentation and for the discussions. So I invite everyone again to open your microphones to thank Sergio for this great talk.
Thank you for having me.
So I will stop recording.